Unlocking the Universe's Secret, Quantum Networks and Quantum Gravity Explained. Quantum networks. The key to unlocking the secrets of quantum gravity? There's no denying that quantum theory has been proven time and time again, both in the lab and through practical applications. But is it always correct? While quantum mechanics can account for 3 of the 4 fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force, gravity has always been the odd one out, preventing quantum physics from being the ultimate answer to fundamental physics. But what if we could finally probe the relationship between relativistic quantum physics and gravity? That's exactly what a team of American physicists at the Stevens Institute of Technology is proposing. They believe that quantum networks could help explore this relationship and provide evidence for the formation of the holy grail of physics. A unified theory of everything. Einstein's curved space. Einstein proposed that mass warps 3D space, creating a curvature through the 4th dimension of time and resulting in a 4D shape that could be viewed as untouched physical space by a human observer. This is the universe predicted by relativistic physics, where mass causes a metaphorical curvature in spacetime that creates the perceived force of gravity. The problem? We're not evolved to perceive this reality. Relativity makes specific predictions about the relationship between mass and the curvature of spacetime, which can be observed through time dilation. This effect occurs at higher speeds or near larger masses, creating differences in the perception of time. While it may sound far-fetched, the adoption of relativity has led to incredible advancements, such as GPS positioning. However, this observable effect poses a problem for quantum mechanics, which has no allowance for it or for gravity at all. The role of quantum networks. Quantum networks allow for direct interaction between quantum events, and the nodes in these networks can be atomic clocks. These clocks can be kept in a superposition where the state of one clock is in perfect sync with the state of another. This could revolutionize fields like encryption, navigation, and precision sensing. But what if the total sync of quantum superposition interacts with the changing flow of time caused by relativistic effects? This is the core question of physics. How do we unify quantum and Einsteinian theory? The paper shows that atomic clocks in a superposition maintained through a quantum network should experience different flows of time, including time dilation caused by speed and gravity, toward a grand unified theory. The new paper illustrates that these atomic clocks could be used to discern the 4D curvature of the 3D manifold in which we live. With a quantum network, we could keep multiple atomic clocks in superposition to discern changes in the flow of time in multiple places at once. If successful, this experiment could inform more research and illustrate the extent to which relativity interacts with quantum mechanics. It's arguable which outcome would have the biggest implications for physics and future research. But one thing is certain. The potential of quantum networks in unlocking the secrets of the universe is truly exciting. Quantum networks. Unlocking the secrets of space-time and gravity. The quantum internet. A revolutionary intersection with Einstein's gravity. Imagine a world where the principles of quantum mechanics and the fabric of spacetime intertwine in ways we have yet to fully understand. This is not just a theoretical dream. It is becoming a reality as scientists unveil groundbreaking research that explores the relationship between quantum networks and Einstein's theory of gravity. The rapid evolution of quantum networking. Quantum networking is experiencing swift advancements worldwide. As a cornerstone of the burgeoning quantum science field, it promises the creation of a global quantum internet. This innovative system would facilitate secure communication on an unprecedented scale and enable the connection of quantum computers across vast distances. Significant strides are already being made to bring this vision to life, both on Earth and in space. In a remarkable recent development, researchers have uncovered that quantum networks possess capabilities that extend beyond mere secure communication. A collaborative study spearheaded by Igor Pekovsky from Stevens Institute of Technology, alongside Jacob Covey from the University of Illinois at Urbana-Champaign and Johannes Borgard from Harvard University, has unveiled a new scientific avenue. Their research, published in PRX Quantum, indicates that quantum networks can be utilized to examine how the curvature of spacetime affects quantum mechanics. This represents a pioneering experimental approach in this field. The uncertainty of quantum behavior in gravitational fields. While quantum theory has consistently withstood experimental scrutiny, its behavior in gravitational fields remains ambiguous. Einstein's general relativity revolutionized our understanding of gravity, portraying it not as a force but as a consequence of the warping of space and time, a phenomenon known as curved spacetime. This curvature leads to extraordinary effects, such as the dilation of time near massive celestial bodies like planets. These phenomena have been validated with remarkable precision and have permeated popular culture, notably in science fiction narratives like the film Interstellar. But how does this alteration in the flow of time influence quantum mechanics? Is it possible that either quantum theory, general relativity, or both may need adjustments where they converge? Although a comprehensive theory of quantum gravity is still elusive, there are indications that quantum principles could be altered in the presence of curved spacetime. However, exploring this frontier has previously been deemed impossible in experimental settings. Innovative methods with quantum networks. In a prior study published in Physical Review Research, Pekovsky and Borgard demonstrated that the time is ripe for experimental inquiries into these questions using quantum networks. They illustrated how two distinct yet complementary aspects of quantum theory and gravity can simultaneously come into play. In quantum theory, superpositions exist, allowing matter to occupy not just specific, defined states but also mixtures of these states concurrently. Quantum computing leverages this principle to create qubits, superpositions of binary bits, 0 and 1. Quantum networks can then transmit these qubits over extensive distances. However, in proximity to Earth, these qubits are also influenced by the curvature of spacetime, as the flow of time itself is altered. The researchers demonstrated that superpositions of atomic clocks within quantum networks would experience different time flows in superposition, paving the way to investigate the relationship between quantum theory and curved spacetime. The interaction between quantum theory and gravity is one of the most formidable challenges in contemporary physics, yet it is also incredibly intriguing, states Igor Pekovsky, Jeffrey S. Inman Jr. Professor at Stevens Institute of Technology and one of the study's authors. Quantum networks will enable us to test this interaction for the first time in real-world experiments. Collaborating with Covey's laboratory, Pekovsky and Borgard devised a concrete experimental protocol. The team demonstrated how quantum effects can be disseminated across network nodes using entangled W states and how the interference among these entangled systems can be recorded. By harnessing modern quantum capabilities, such as quantum teleportation, the transfer of a particle's quantum state to another particle, and entangled bell pairs, maximally entangled states of 2 qubits, within atomic arrays, it becomes feasible to test quantum theory in the context of curved spacetime. Rethinking quantum network significance. We operate under the assumption that quantum theory is universally applicable, but we truly do not know if this is accurate, remarks Pekovsky. It is possible that gravity alters the functioning of quantum mechanics. In fact, some theoretical frameworks propose such modifications, and quantum technology will be capable of testing these ideas. The findings of Pekovsky, Covey, and Borgard illustrate that quantum networks are not merely practical tools for a future quantum internet. They also offer unique opportunities for exploring fundamental physics that classical sensing cannot achieve. At the very least, we now have the potential to test how quantum mechanics behaves in curved spacetime. References *. Probing Curved Spacetime with a Distributed Atomic Processor Clock by Jacob P. Covey, Igor Pekovsky, and Johannes Borgard, 2025, PRX Quantum. DOI 10.4855/AR14.2502.12954. Testing Quantum Theory on Curved Spacetime with Quantum Networks by Johannes Borgard and Igor Pekovsky, May 27, 2025, Physical Review Research. DOI 10.1103/PhysRevResearch.7.023192. Stay updated on breakthroughs *. Never miss a significant advancement. Subscribe to the SciTech Daily newsletter. Quantum Reality Shaken: How Gravity and Spacetime Alter the Quantum World. The foundations of quantum reality are shaking. New research reveals how gravity and spacetime significantly influence the quantum realm. In a nutshell, microscope researchers are investigating the intricate relationship between quantum mechanics and gravity through the use of sophisticated quantum networks. Milky Way. These quantum networks have the potential to create a worldwide quantum internet, employing qubits and entanglement to ensure secure communications. Magnifying glass tilted left. The goal of this research is to explore whether gravity can modify quantum mechanics, which could lead to a comprehensive theory of quantum gravity. Rocket. Such advancements could transform our understanding of the universe and reshape the very foundations of physics. In an exciting new chapter of physics, scientists are diving deep into the fascinating connection between quantum mechanics and gravity. Their groundbreaking work could unlock a more profound comprehension of the fundamental laws that govern our universe. By leveraging advanced quantum networks, these researchers are on a quest to discover how the interaction between the curvature of spacetime and quantum theory might bring us closer to a unified theory of quantum gravity. As they challenge the limits of contemporary science, the potential ramifications for technology and our understanding of the cosmos are immense. This initiative could redefine both theoretical science and practical applications in ways we have yet to envision. The relationship between quantum theory and gravity. The connection between quantum theory and gravity has captivated scientists for decades. Quantum networking is emerging as a crucial instrument in this investigation, with the capacity to revolutionize global communication systems. Unlike conventional methods that depend on electrons and photons, quantum networks utilize qubits and entanglement to transmit information. This innovative approach could lead to a globally interconnected quantum internet, providing unparalleled security and reach. In a recent article published in PRX Quantum, researchers Igor Pekovsky, Jacob Covey, and Johannes Borgard emphasized the potential of quantum networks to examine the relationship between quantum theory and gravity. Their research introduces a novel protocol that employs entangled W states, demonstrating how quantum phenomena can be detected across network nodes. By applying advanced techniques such as quantum teleportation and entangled bell pairs, these scientists are investigating how quantum theory functions within the context of curved spacetime. Could gravity influence quantum mechanics? The noticeable gap between Einstein's general theory of relativity and quantum mechanics presents one of the most compelling challenges in physics. Quantum mechanics examines the behavior of matter at atomic and subatomic levels, while classical physics addresses larger objects. This distinction raises an intriguing question. Could gravity affect quantum mechanics in ways that remain elusive to us? Current experiments are designed to ascertain whether variations in spacetime could influence atomic and subatomic behaviors. Igor Pekovsky points out that while quantum theory is generally accepted as universally applicable, gravity might indeed alter its effects. The ongoing research utilizing quantum networks suggests that these networks could serve not only future technological purposes, but also become essential tools for probing fundamental physics in ways that classical computing cannot achieve. Quantum networks, a pathway to a unified theory. Quantum networks are not merely technological wonders. They are also powerful instruments for scientific inquiry. By enabling the examination of quantum effects within curved spacetime, they may help bridge the divide between quantum mechanics and general relativity. This could lead to the long-sought unified theory of quantum gravity, providing insights into the fundamental essence of the universe. The innovative application of entangled states and advanced quantum techniques by researchers highlights the significant promise of quantum networks. These networks facilitate the observation and analysis of phenomena that classical methods cannot address, establishing them as a cornerstone in the pursuit of a unified theory. As these networks develop, they hold the potential to transform both scientific understanding and practical applications, opening new horizons in physics and technology. The future of quantum exploration. The ongoing investigation into the relationship between quantum mechanics and gravity exemplifies human curiosity and creativity. By harnessing the capabilities of quantum networks, scientists are forging new paths for exploration and discovery. As they continue to delve into the complexities of spacetime and quantum theory, the opportunities for technological progress and scientific enlightenment are boundless. As we stand on the threshold of a new era in physics, the potential for quantum networks to reshape our understanding of the universe is both thrilling and profound. Will these endeavors ultimately lead to a unified theory that reconciles the principles of quantum mechanics with gravity? The journey is just beginning, and the answers may fundamentally alter our perception of reality itself.